Okay, so this is Lecture 2, Section 7, Part 7. And this lecture concerns the definition of the derivative of a function, and we'll discuss rates of change. So we're going to basically motivate the definition of a derivative of a function using a geometric approach, and as well as the rates of change, what we mean by that. So I'm going to start off by showing an illustration. Let me pull it up from the lecture notes. And I believe this illustration may be in your text in section 2.7. I'm not sure. But nevertheless, an equivalent one is in your text, so based on whatever edition you may have. All right, so consider this illustration. And so what's going on in this picture? Well, the black curve, of course, is your f of x in the xy plane. And notice the blue line segment that connects the point P to the point Q. And the point P is given very specific coordinates. The abscissa of P, of course, is A, x equals A, and then the ordinate is f of A. And the intent of this drawing is to demonstrate that Q is some arbitrary point on the graph. And by arbitrariness, it's because the abscissa of Q is x. And x is unspecified at this point. All we know is that x is not A. And then if x is the abscissa, of course, f of x is the output. So there was a little bit of confusion about why are we specifying the coordinates of a point in this format, x f of x. Well, it just denotes that it's any arbitrary point selection on f of x, where q, of course, is not P. And moving along, we see that we have an incremental change in y from P to Q, and that is f of x minus f of A is the incremental change in y. And then there's an incremental change in x, which is x minus A. So we have basically a situation going on here where we have delta y over delta x. Okay. And of course, what you should recognize is that the blue line segment is a secant line, okay, connecting two distinct points on the curve, and that this delta y over delta x is the slope of a secant line. Now let me pull up another illustration. Bear with me while I grab it from the text. All right, so in this illustration, what's going on here is I'm showing a sequence of secant lines, right? Each secant line is shaded in blue. So here's the first secant line right here connecting P and Q. Note that Q, the arbitrariness of Q allows us to specify Q on different locations on the graph f of x. Here's the second secant line, and then here's the third secant line. And so what's the dynamic here? Well, we're moving Q closer and closer to P, where the abscissa of Q is greater than the abscissa of P. All right? So, and that's indicated by the direction of the yellow arrows. And what the intent of this drawing is to show is that as Q advances toward P, the secant line converges toward a tangential line, which is shown in red. Right, so we've discussed this many times in the past, and so we'll talk more about this. We use this mainly to, we use this illustration to emphasize how to compute the slope of a tangential line at a point P, where we only know the coordinates of one point, and of course, we use point slope form to calculate the equation of line t, knowing only the coordinates of one point. And the way we deal with that is we approximate the slope by the slope of a secant line, where the secant line almost matches up with the tangential line. All right, so let's talk about the tangential line. All right, the tangent line to y equals f of x at p, at the point P, which coordinates are a, f of a, is the line through T with slope, and let me give you the equation. I'll use the equation editor here, with slope equal to m, which is equal to the limit as x. Okay, now remember, x is the abscissa of Q, a is the abscissa of P, so x is approaching a of what? Okay, so the ordinate of Q minus the ordinate of P divided by, try it again. Okay, so this would be the ordinate of Q minus the ordinate of P divided by the abscissa of Q minus the abscissa of P. All right, so this would be the slope of your tangential line. A very important formula. All right. And in the past, I believe we used a function table to calculate the slope. But now we're transitioning now to calculating the slopes of these tangential lines using this limit formula. Okay, and and the proof of this limit is shown in this illustration right here. We're walking Q towards P, at least from the right-hand side. Now, notice I didn't specify if this were a left or right limit. So implicit in this definition for slope is that the left and right limits must be the same because of x approaching a. Remember the theorem that says that this limit is true if both the left and right limits are the same. Okay, and that's what we're assuming here. It's implicit in this definition. All right, so I'm going to modify this slope a bit. We can, through a change of what's considered to be a change of variable, why don't we let h, the variable h, equal to x minus a, which is the denominator in the equation for the slope. All right, and so how does that transform the equation? Well, if h equals to x minus a, okay, then what is x equal to? Then x is equal to h plus a. And so I'm going to make these substitutions into the equation of the slope of the secant line. So the slope of the secant line would equal to, in this case, it would be the slope of the tangent line without the limit. All right, so that would be x, which is now h plus a, minus f of a divided by h. All right, so that would be the slope of the secant line. And this should be familiar to you. This happens to be the definition of the difference quotient at a. So you may recall that term from algebra. So this is the difference quotient. Okay. So knowing this, we have a problem. We can go back and revisit a problem that started this chapter, and that is find the equation of the tangent line to the parabola y equals x squared at the point 1, 1. All right. So in this case, okay, so to solve this problem, using the limit laws, we can say that if a is equal to 1, okay, because a is the abscissa of P. All right, so identify the abscissa or x-coordinate of P. All right, so now using, oh, okay, and of course f of x is equal to x squared. So now, so the equation of the tangent line, we use point slope to find the equation. That would be y minus 1 times slope times x minus 1. And as you know, the work to be done is to calculate the slope of the tangent line. And so using the previous constructions, we know that the limit of the tangent, the slope of the tangent line, m is equal to the limit as x approaches a, which in this case is 1, of f of x minus f of a, which is 1, divided by x minus 1. Okay, and so now we make the appropriate substitutions. So that's equal. The limit as x approaches 1. Now f of x, of course, is x squared. And f of 1 is 1 divided by x minus 1. All right, and so that's a classic limit problem. So we can, it's an indeterminate form. So we know that the limit is going to evaluate to some number. Okay, and so this would be, we can factor the numerator. All right, and so we get a cancellation of these two factors. And so once we get a cancellation, we're left with a polynomial, and then we can use direct substitution. And after direct substitution, that's 2. So therefore, you readily get the equation of the tangent line to the parabola at the point 1, 1, which is this. Okay, and so that's a lot less work than having to build a function table. All right, so we can express the slope of the tangent line in terms of the difference quotient of a function. So let me pull up an illustration for you. Okay, so let's focus on the illustration initially. So again, here we have the black curve as our function. And what we've done here is we've let, well, we haven't, okay, let me explain the replacement here. We let h equal to x minus a, okay? And so if h is equal, so that means that what I'm accentuating here, this distance is h right there. Okay, And so if this is x right here, which is the abscissa q, so x minus a is equal to h. And so if we make the substitution, as I did previously, the abscissa of q then becomes a plus h, and the ordinate becomes f of a plus h. Here's the point P, and then h, of course, is the width of the this width right here, and then f of a plus h minus f of a is this height right here. And so we have an equation for the slope of the secant line, which would be this without the limit. Okay, so this would be the slope of the blue secant line. Okay, so this is the slope of the blue secant line. And then when we tack on the limit and we drive h toward a, then we get the slope of the tangent line, which is red. Okay, so the limit as the denominator approaches 0 of the difference quotient of a function will be the slope of the tangent line at x equals a. Okay, so a very, very important result. So using this, let's use this formula now to solve another problem. Let me pull up a graph for you. Okay, I need to step away from the recording for a few minutes, so I'm going to put a note here. Okay, so, and when I get back, I'll put a note saying recording resumed. So stand by. I'll go to the office. Okay, so recording resumed. Right. Okay, so the question asked is, we're asking now is, the blue curve is the graph of the hyperbola y equals 3 over x. And the question we're pursuing is, we want to find the equation of the tangent line to the hyperbola y equals 3 over x at 3, 1. Okay, and this is your point P. P is your here's your points. All right, and so the equation then would be y minus 1 is equal to slope of the tangent line times x minus 3. And this time we're going to calculate the slope of the tangent line based on the limit of the difference quotient. We're not going to use the delta y over delta x. We're going to use the difference quotient. And this is probably how we'll do it for the most part from here on out. Although there will be a few occasions where we'll use delta y over delta x. Okay, so we'll calculate the slope of the tangent line by taking the limit as h approaches 0 of the difference quotient. And so, of course, in this case, a is 3. All right, so we wire in 3 into the equation for the slope of the tangent. And then we replace f with its definition. So f is 3 over x. So f of 3 plus h will be 3 over 3 plus h minus 1, because f of 3 is 1, divided by h. And so we evaluate this limit. And so we can multiply upstairs and downstairs by 3 plus h to simplify this complex fraction. So we'll have 3 minus 3 plus h divided by h times 3 plus h, right? That's a minus, not a multiplier. Okay, sorry about that. Okay, so this would be the limit as h approaches 0. Simplifying the numerator, we're left with minus h. And we'll leave the denominator as is, because if we do, you can see there's going to be a cancellation. So cancel the h's, and then we can use direct substitution, because now 0 is in the domain of the remaining rational function, and so that's equal to negative 1/3. So that's the slope of the tangent line, and then so we wire that in. So the equation then of the tangent line becomes using point slope. All right, and then after simplification, we get what? Negative 3y plus 3 is equal to x minus 3. So we have 6 is equal to x plus 3y, if you want to simplify it, if you want to mess with the algebra. I'm not that strict on simplifying it. This expression right here is more than enough for the answer. Okay. All right. So now we'll revisit physics problems, and so we'll talk about velocities. So recall from previous notes that we have average velocity and instantaneous velocities. And now we can express instantaneous velocity in terms of a difference quotient. So do I need to bring up some illustrations? Yeah, so I'll pull up some pictures. Math through pictures. I think students appreciate that, so we'll give it a go. So let's talk about this picture. All right, so look at the first illustration. And here we have a t-axis. This is t. And this first red point is the position of some object moving in motion at time t equals a. And then what happens is time goes by, and then the object changes its position at time t equals, and that's at h, a plus h. It looks a little bit truncated there, so this will be a plus h. All right, so the total time traveled is h, and the distance traveled would be f of a plus h, the final position minus the initial position. So this would be the displacement, and then this would be the time, right? And that's shown here as well through these markers. And of course, we're referencing it with respect to the origin on the t-axis. Here we have a more complicated function, which shows position s right here. Here's s as a function of time. And so here again, we have our t equals a with respect to the origin. And then time lapse a plus h, so the total time we're analyzing is h, say seconds for instance. And then the displacement from point P to point Q in terms of a and h. And so the average velocity, again, is the slope of this blue secant line. So this is your average velocity, okay? And so there's a very useful formula. And then now we can talk about the instantaneous velocity and with respect to this figure. So I'll call instantaneous velocity, it's equal to the limit as h approaches 0 of the difference quotient of the average velocity. Okay, so look at the formula for the average velocity. It's a difference quotient, right? So you should recognize this as a difference quotient from your algebra. All right, and so if we take the limit as the denominator approaches 0, we get the instantaneous velocity. All right, and so now we can revisit the CN tower, dropping the object from the top of the CN tower. So let me paste that in here, so I don't have to rewrite it all the time. All right, so here's the problem. Okay, so this symbol right here, an S with a P, okay, this means suppose. I don't know if I've explained that in the past. That's my shorthand notation for suppose. That is not a math symbol, that's my own construction. Okay, all right, so for example, suppose that a ball is dropped from the upper observation deck of the CN tower, 450 meters above the ground, just as before in one of the previous lectures. So we're asked to find the instantaneous velocity at any time t. So the formula, the position, this is the position function with respect to t, and the platform from which you're dropping the ball is this. And so the velocity at any time t, which I denote as variable a, is the limit of the difference quotient of the position function. So velocity is the limit of the difference quotient of the position function. So f, I think in the past I've written as s of t, which is the position function, the position of the ball with respect to the platform at time t. And in this case, I've changed t to a. All right. Okay, and so plugging in the equation for f, we get this, and now what remains to be done is to simplify this limit. Okay, so we can simplify it, and this will be, you'll have to draw on your knowledge of algebra now. We'll have to completely expand this binomial square. So I'm going to trust this. You know this reasonably well. All right, and then we simplify this. So that's 9.8 AH plus 4.9 H squared divided by H, and then we can simplify this rational function. The limit as H approaches 0, and we get some cancellations of the H's. And what results is basically a polynomial in H. So now we can use direct substitution, and that would be 9.8a. So whatever t is, you can plug it in for a and get the instantaneous velocity. So remember, from the illustration, do I have it? I don't have, okay, I don't have a, well, we can use this one. Remember that the instantaneous velocity, right here shown in this picture, is the slope of the tangent line at a particular time t equals a of f, which is the position function. Okay, so keep these concepts in mind when you deal with these kinds of problems. All right, so we have that. Right. Now, the next question then is, how fast is the ball moving when it impacts? That is, when it hits the ground. All right. So how do we answer that question? Okay, well, we know the position function. So we know S of t, position, is equal to 4.9 t squared. All right, and when it impacts, it will be 450 meters from the deck, the upper deck. Okay, so we know at what time it impacts. So if we solve for t, so t is equal to what? The square root of 450 divided by 4.9. Okay, and that's approximately 9.6 seconds. All right, and so we know the velocity. The velocity, the instantaneous velocity at any time t is equal to 9.8 t, and so we just take 9.6 and we substitute it in. So v of 9.6 is equal to 94 meters per second. Okay, so that's how fast it hits the ground. All right, so now we can talk about the definition of a derivative of a function. Okay, so the derivative of a function f at x equals a is defined as f prime of x. And there's a formula for it. It's a limit. Okay. So let me write the limit using the math tool. The limit as x approaches a, well, we'll use h because we're dealing with difference quotient. The limit as h approaches a of the difference quotient. Okay, so that would be f of a plus h minus f of a divided by h. So that's the derivative of a function. That's how you find it. And what does it mean? It is the slope, the derivative is the slope of the tangent line, or not, I'll use a, of a tangent line to f of x at x equals a. So that is the geometric interpretation of what a derivative of a function is. Now, if you don't like using difference quotients, the alternative and equivalent definition is this. We can express the derivative in terms of x if you don't like using h, and we can use the delta y over delta x style of representing the derivative. So this would be delta y over delta x. Now, provided that you take the limit as x approaches a. Okay, so these are two alternative definitions that we will use quite extensively. All right, so now we can calculate derivatives of functions. So let's do that. Let's find f prime of a if f of x is equal to x squared minus 8x plus 9. All right, so we can use the difference quotient technique. F prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a divided by h. Now, I assume that you're confident with using composition because we have to compose f with a plus h in evaluating this difference quotient. All right, so this is equal to the limit as h approaches 0 of, okay, so I'll plug in a plus h into f. So I'll have a plus h squared minus 8 times a plus h plus 9 minus, okay, next I plug in a into f of x. So that would be a squared minus 8a plus 9. And all of this divided by h. And now I have to take the limit as h approaches 0 of this rational function. So that means I have to do quite a bit of algebra here. So we proceed. So limit as h approaches 0 of, okay, complete the binomial square, a squared plus 2ah plus h squared minus 8a minus 8h plus 9. And then we'll distribute the negative sign. We'll get rid of the brackets. Minus a squared plus 8a minus 9. divided by h. And so that would equal to the limit. We'll simplify the numerator now. The a squares cancel. The 9's cancel. The 8a's cancel. And so we're left with 2ah plus h squared minus 8h over h. Okay, and now we can get some cancellations in the h's. So this will be the limit as h approaches 0 of 2a plus h minus 8. And now we have a polynomial in h, so we can use direct substitution. So this would be 2a minus 8. So that would be the slope of the tangent line to f at any value x equals a. All right, so let's see here. So suppose you want to find, well, let me post a technical note here. So let me grab that. All right, so how can we make use of this calculation we just made? Well, let me show you. This page, paste. Okay, so based on the calculation we just made, the tangent line to y equals f of x at the point a f of a is the line through the point a f of a whose slope is f prime of a. And so the equation of the tangent line to this parabola at, say, 3, negative 6, right, is y minus, okay, minus 6, and then we plug in our slope formula in terms of a, which is 2a minus 8. Okay, this is your m. Remember, this is your m. We just calculate it using the difference quotient times x minus 3. And then once we get this stood up, then we just say, okay, a is equal to 3, and the 3 comes from here, right here. So that's how you would use it. All right, so enough said with derivatives for now. I want to talk about rates of change, which are applications which use derivatives. So I want to pull a figure in. So let me do that. All right, so we talk about the average rate of change of y, and WRT means with respect to. So the average rate of change of y with respect to x on an interval x1, x2. And in the literature, we call this delta y over delta x, or the change in y over the change of x. And the average rate of change is the change in y, f of x2 minus f of x1, divided by x2 minus x1. Shown in this figure, and it's basically the slope of the secant line. Okay, so here, instead of using precise coordinates for P, I'm going to let P be a floating point, arbitrary selection, and I'll let, as well as letting Q be an arbitrary selection. And so here's my x1, here's my x2. The average rate of change, MPQ, is the slope of the blue secant line. And then, as usual, the instantaneous rate of change is the slope of the tangent line at P. So we're no longer going to have restrictions on the coordinates of P. We're going to let P be any arbitrary point, and we're going to let Q be any arbitrary point on the graph of the function. And then, of course, as usual, the red line is your tangent line. So the instantaneous rate of change then is, well, the limit as delta x approaches 0 of delta y over delta x. This is the classical Newtonian definition of instantaneous rate of change. And then we can translate this formula in terms of x1, in terms of the abscissas of P and Q. So as the abscissa of Q approaches the abscissa of P, we get fx2 minus fx1 over x2 minus x1. And then finally, we get an alternative definition. The derivative f prime of a is the instantaneous rate of change of y equals f of x with respect to x when x equals a. All right, so there we go again, a duplication of definitions. All right, so now we can do some examples. So next page. So let me pull one from the lecture notes. And this will be an example of an application of the instantaneous rate of change. And this example is worked out already, so we can go through it relatively quickly. Okay, so in this case, a manufacturer produces bolts of fabric with a fixed width. Right? The cost of producing X yards of fabric is C, which is equal to F of X dollars. Right? So in this case, and I believe there will be some web-assigned problems very similar to this. So the derivative of F is the instantaneous rate of change of C with respect to X. Okay, and the derivative of F, the definition is called the marginal cost, which is the rate of change of production cost with respect to the number of yards produced. Okay, so the rate of change of production cost. So what it means is that as you produce so much quantity of product, in this case yards produced, the production cost will change as the number of yards changes. So it may increase or decrease depending on the circumstances of the manufacturing process. So mathematically, we have the derivative of the function is the limit as delta x approaches 0 of the change in cost with respect to the change in the amount produced. And that would be in dollars per yard. So for instance, f prime of 1,000 is equal to 9. And what this means from the manufacturing perspective is after 1,000 yards of fabric manufacturing, the rate at which production cost is increasing is $9 per yard. Okay, so that is the cost is increasing 9 times faster. So I didn't, okay, yeah, so there's no, I didn't specify F is, what F is, but what it means is after so many yards of production, your production costs are increasing. So you have to be careful and monitor this because the revenues may start dropping after so much production increase. Okay? So that's what that means. And I think in WebAssign you'll be given a definition for F, and you just calculate this F prime of X, and then you'll make this similar interpretation. Okay? So let's do another example. Let me pull it from the notes. All right, so let's follow this example. So let D of T be the national debt with time. So look at this table of information. So in 1980, the debt was this, probably ostensibly in billions of dollars. 85, we had $1 trillion debt. 90, we had a $3 trillion debt. 95, we had a $4 trillion, and then in 2000, we had a $5.6 trillion debt. So D prime of 1990 is the rate of increase of the national debt in 1990, right? And so we have this delta y over delta x notion. So we have debt with time. We want to calculate the average rate of change of the debt with time. So this is this table right here. This is the average rate of change. it's basically delta y over delta x. So it's delta, in this case, delta d over delta t, right? And then in this case, t is equal to, our a value is equal to 1990. That's our reference point. So dt minus d of 1990, there's your a value, right? Over t minus a, there's your a value, okay? And so we start off at 80, we plug in these different numbers, and we get the average rate of change of the debt in 5-year increments. And of course, when we want to know the instantaneous rate of increase in 1990, we have to take the derivative of the debt function and evaluate it at 1990. And so all we do is we take the limit as t approaches a to get the instantaneous rate of change of the debt function in 1990. And so we could, in 1990, we could say that the debt was growing at a certain rate. Okay, so that's all that means. And of course, again, in this case, we don't have a function for d. All we have is a table. Okay, a couple more examples. So here's an interesting example from the book. So here we have a graph that shows the influence of temperature T on the maximum sustainable swimming speed of coho salmon. This might be of interest to folks in Alaska. So what is the meaning of the derivative? All right, so what we have is the y-axis, S, is the speed of the salmon, and then T is the temperature. So what is the meaning of the derivative? All right, so the derivative, the slope of the tangent line to a particular point, that means okay, what? S of so not H, but yeah, S of T plus H minus S of T divided by H. So the derivative is the slope of the tangent line, which is change in speed divided by change in temperature. Okay, so that's the meaning of the derivative. It means that as it's the time rate of change of the velocity or the swimming speed with respect to temperature. That's the derivative. And then S prime of 15, well, it's kind of hard to do on this graph, but S prime of 15, I guess we could kind of estimate it using the the average swimming rate or something like that. Let's see how we can calculate that. So a good estimate would be, since we don't know the function, we could just use the delta y over delta x. So how about, in this case, delta s over delta t. So that would be, say, we use 15 and 10 as our time interval. So s at 15 would be what? Roughly 30. So that would be 30 minus, say, s at 10 would be 22 divided by 15. I'm guessing here. So that would be what, 8/5. So what it means is for every 5 degrees rise in temperature, okay, for every 5 degrees rise in temperature, the swimming rate would go up by 8 centimeters per second. So you warm the temperature, the swimming rate increases on this interval, so at least. On this interval that I've accentuated here. Increase the temperature, the swimming rate increases. Now at S equals 25, okay, if the temperature increases here, then the swimming rate starts to decrease. All right, so we have a negative slope here. Okay, so that's all that means. Okay, so you may have a WebAssign problem or two regarding this kind of problem. All right, so that's it for section 2.7. We have one more section left for this chapter, and I certainly hope that you're nearing completion of your project number 2. And what else? Your WebAssign homework. I'm hoping that you'll have completed that. Again, email me if you have any questions or you need to see some techniques for solving some of the more complicated WebAssign problems. And we'll have section 2.8 next, and we'll review for our test on chapter 2 as well. So please monitor your email and other messages for details on how we'll